Let's do a quick review of the previous lecture, as usual. So last time we kind of started, going into the details of sonar in terms of the different types of sonar systems for robotics, of course. And then we kind of did a taxonomy of sonar, if you will. So starting with what type of waveforms these systems use for sensing, the breakdown is pretty clear. So either your system sends short pulses, and there's kind of like a silent time between two consecutive pulses, and during that time, it basically is hearing back for the echoes from the environment, or it is continuous, so that would be a pulse echo sonar or ultrasonic sensor, or it's continuously transmitting signals. And so there's no silence time, basically. It's continuously transmitting, and that's a continuous transmission frequency modulated, or CTFM sonar, also called FMCW sonar, frequency modulated continuous wave. This term FMCW is less used in sonar terminology. Mostly it's called CTFM. But when we talk about radar, you would see that there's like systems of basically the exact same type of architecture in radar, and those are called FMCW. So that's why I included, so you kind of, start identifying these, though different fields use different terms, they are the same type of systems or principle of operation. Then we looked in detail at pulse echo sonar in terms of what types of pulse waveforms they use. There's many different pulses, so there's no standard table of just a few pulses that are used. Every sensor manufacturer, they kind of come up with their own version of pulses. You can also design your own. So we looked at a few, but the big divide here is either they're narrowband pulses. So those are basically kind of like a pure sinusoid with some amplitude envelope applied to them, or they're wideband pulses, which are typically much shorter, and then they take up more spectral bandwidth basically in the frequency domain. And then in terms of how you detect range, the ranging algorithms for pulse echo sonar, we also looked at two main types of algorithms. The first one was a threshold-based ranging, which basically you just rectify and integrate your received echo, and as soon as the output of your integrator passes a predetermined threshold, you declare a detection. Very simple algorithm. It can even be fully implemented in analog, so you might not even need to use like an ADC and a DSP. You can do it much simpler, but it comes with all sorts of caveats in terms of specifically the error in ranging has dependency on the amplitude of the received echo and also on the angle of where the target is, and in certain cases we saw that the error can blow up. So there's a trade-off there, right? You get something very simple, you can get it up and running quickly and cheap, but it's not the best performing algorithm for you. Or you could do basically what we learned in GPS. You can do matched filtering or correlation-based detectors. And for that, you basically take your received echo and correlate that with the waveform that was transmitted. And at the output of that correlator, there's going to be a peak. And the index of that peak corresponds to the round trip time of flight. And then for this, as we know, of course, you would want to, if you're using match filtering, you would want to use waveforms or pulses with good correlation properties that give you like a nice sharp peak with low side lobes. So you could do, for instance, Barker codes are a good choice that are used. PN sequences also work, of course, but they're a bit overkill, I would say, for sonar, because for sonar we're doing with short range applications. You don't need codes with very high SNR. Okay, and then, so this was about pulse echo sonar. Then we started talking about CTFM sonar. And the CTFM this FM part of it, the frequency modulation, is there because these systems typically send a very specific type of waveform, which is a linear frequency chirp. I mean, so what a linear frequency chirp is it's basically a signal in the time domain, and it's designed such that if you calculate the instantaneous frequency of the signal, it varies linearly over time, right? So this plot, which is a bit of a unusual way of visualizing the signal, because either we're used to like looking at the signals in terms of their amplitude versus time, or we look at their Fourier transform basically. This is something in between. So your vertical axis is the instantaneous frequency, horizontal is time, okay? But it is the most intuitive way of thinking about these signals. So the instantaneous frequency, let's look at the black first. That's the basically waveform that you transmit. At time 0, it starts at some frequency f0, and it just linearly goes up. It could also go down. That's just a choice of slew rate, right? You can also ramp it down. Doesn't matter. It's the same principle. So with some slew rate b, your frequency basically linearly goes up, and then you transmit for a pulse duration or a waveform duration of big T, and then you repeat. So I've only drawn one, but basically right after that, because it's a continuous transmission system, so as soon as you finish the first one, you start the second one, basically. But let's just look at one for now. So you start from f0, you go to f0 plus b is your slew rate in hertz per second, right? Times t, which is the duration. So that delta frequency here, that's the overall bandwidth that your pulse takes up, and it's called it's denoted by big B for the bandwidth, which is equal to basically slew rate times time. B times T is the total bandwidth. What you receive is going to be just a delayed version of what you transmit. I mean, there's attenuation also, but if you look at the frequency of it, it's just going to be the same linear frequency chirp or ramp, just delayed by some round trip time of flight tau, right? So you essentially get the same thing, and really the beauty of this technique is that now if you look at the difference in the instantaneous frequency of the waveform that you transmitted and the echo that you've received, first of all, that delta frequency, I mean, these are two parallel lines, right? So the delta frequency is going to be constant for the duration that you're receiving the echo, okay? And that delta F, as we showed, is proportional to tau. In fact, it's exactly equal to your slew rate times tau. Very simple linear relationship. So it's just B times tau. So B is known, right? That's a choice that we make for the waveform that we're transmitting. So all we need to do is estimate the difference in the instantaneous frequency of the echo that's received compared to the original waveform that was transmitted. Once that delta F is known, you divide by B, you get your time of flight tau. And we know the time of flight. From that, we can basically estimate range. You just divide your time of flight by 2 to go from round trip to one way, and then also divide by the speed of sound, and that gives you range. Okay. So now today we are going to basically start by looking at how to find this delta F, because that's at the core of how CTFM sonar works. Any questions before we continue? Okay. So we were looking at the system block diagram for a CTFM sonar, and we said that really the magic happens at basically this block here, which is called a mixer or a down converter. And what happens here is that we feed it the echo signal that we've collected back at the receiver, and S of t, which is the basically the transmitted chirp, right? So that's the chirp that we send, and then it basically outputs some signal which we call SIF of t, which is our intermediate frequency signal. And if this block is designed right, that SIF of t should have a frequency at delta F, which is the difference between the transmitted and the received echo frequency. And in fact, mathematically, it turns out that the operation that block needs to do is very simple. It's basically just a complex multiplication. So what that, and that's why we show it as a multiplier, because it's actually exactly multiplying those signals. So what it does is basically it multiplies the complex conjugate of the echo that you have received by SFT, which again, SFT is that chirp waveform that we generate and send out. Explicitly, we can break down the echo into two parts. So it has, the echo signal has an amplitude that, as we know, depends on range and the angle of the target. So it depends on theta and rho. But the time dependency of it is just a delayed version of the transmitted chirp. Right? And why the star? Because we are taking like that mixer block is conjugating it. So that's an operation that happens inside the mixer. So you get basically S star of t minus tau times S of t. And now we can plug in the expression that we have for that chirp signal. Remember, let me first go to the next one. But remember, S of t was basically exponential of something like j2 pi some f0 plus bt over 2 times t. So this was the, mathematically what the linear frequency chirp is. So you just plug that in, right? So this here basically is our S of t, and this term is the S star of t minus tau. That's why this has a minus sign. And then a lot of things simplify. It's just, two exponential terms getting multiplied out, and you do the math. Some terms cancel out, but what you're left with is, of course, the mu, which is the gain of the amplifier, and this echo amplitude just carry over. But we're concerned with, the time dependency of it, right? So what you get at the end of the day, you get e to the j2 pi. Let me go one step further. Inside the exponent, you get this b times tau times t, and that's the only term that has time dependence. And you get something that depends on like f0 and b and tau, but there's no t dependency in it. So that's just a constant phase for us, right? So we can basically refactor this, and this b times tau, we call that our delta f. Right? And everything else, just call that phi of tau. It's just a constant phase, basically, for the duration of the received echo. And so we see that this SIF, the intermediate frequency signal that's coming out of the mixer, exactly has the property that we want. It's basically the time dependency of it. Like if you ignore everything else that is not time dependent, like the echo amplitude and that constant phase, the SIF of t is proportional to e to the j2 pi delta f t, which is exactly what we want. So this signal has instantaneous frequency, or it's actually just a constant frequency that is proportional to the time of flight tau, right? So basically at this point, we have a sensor, right? Because that block diagram that we showed, if you build that, the intermediate frequency that we get, if I just go back to the block diagram real quick so we can look at it together. So this intermediate frequency signal that we have, it's going to get filtered and passed through an ADC, but then the discretized version that we have, this signal has a frequency that is proportional to the time of flight. So now to estimate time of flight and ultimately range, all we need to do is to estimate the frequency of the IF signal, right? And again, as we know, the rho, which is the range, is going to be proportional to the frequency delta f of the down-converted signal via this expression. Where is this coming from? Well, we know rho is basically the time of flight times the speed of light over 2, and then we have just plugged in for tau, we have plugged in this expression, which is delta f over b. So that's our time of flight. Okay. So really, the magic or the power of this idea of CTFM or FMCW is that we have converted a range estimation problem to a frequency estimation problem. So now we just need to estimate the frequency of the signal in DSP. And as I said last time, there is tens or possibly hundreds of algorithms for frequency estimation. If you just go on Google and search for spectral estimation or frequency estimation, you would see tons and tons and tons of papers. I mean, some of them go back, many tens of years, because it's a problem that has been studied in statistics and later in electrical engineering for many years, and people have come up with really beautiful algorithms for spectral estimations. Different algorithms, they have different trade-offs. Some are more accurate but more computationally complex. Some are simpler, not as accurate. I mean, you get all sorts of trade-offs between them. We're going to look at the simplest and most efficient one, which you all already know about, which is a Fourier transform, right? I mean, what Fourier transform is good at is telling you the spectral content of a signal. Now, if you have a signal which basically has just one frequency in it, and you look at its Fourier transform or the magnitude of the Fourier transform, it will show a peak at that frequency, right? So basically in DSP, with our simple algorithm, we just take the Fourier transform of the IF signal. So this digitized IF signal comes in. You take the Fourier transform of it, okay, and you get what we call big S IF of k. And then you find peaks, or you look at basically the magnitude of the Fourier transform, and you look at the peaks, right? So what you would typically see if this plot down here is the FFT of SIF, so it's also plotted in log scale, so that's why we call it dB here. So to be very concrete about it, what is being plotted is 20 times log 10 of the magnitude of the FFT of SIF of n. That's what this is, and that's why it's in dB, because we're taking 20 log. Why dB? I mean, it's just makes a nicer plot. That's why. I mean, there's really you could plot it in linear scale, if you will. But the point here is that well, you look at your FFT, and at some index k hat, you're going to see a peak, right? And that index, or the frequency of that index, is basically the frequency of the IF signal, and then we can convert that to time of flight and range. How do we convert that to frequency? Well, this simple formula, right? As you know from Fourier transforms, well, you get an index, right? But to go from the index to the actual frequency in hertz, all you need to do, so if your signal, or if one chirp after the ADC had n samples in it, so we are basically taking an n point FFT here. That's why our k index goes from 0 to n minus 1. We're just looking at one period of the FFT. The frequency varies linearly here, right? So all you need to do to go from your index to the frequency, you divide that by n and multiply that by fs, which is the ADC sampling rate. And that gives you your delta f hat, which is your estimate of the frequency of the IF signal. Okay? And what is your range estimate then? You just basically do delta f hat times the speed of sound divided by 2 times the slew rate, and that would be the range of your target. Okay? And that's it. I mean, the algorithms for CTFM are really this simple. It's just one FFT you do, look at the magnitude, take the peak, and convert the index of the peak to the frequency, and then convert the frequency to time of flight and range. And it's all just, just linear transfer, just a bunch of scalings, basically, that you need to do in between to go from index to frequency to time of flight to range. Okay, make sure this here makes sense to you. If it doesn't, let me know. Let's talk about it. Does this make sense, how we're converting the frequency, right? Because, again, when you do the FFT, for your index, 0 index corresponds to 0 frequency, and index n corresponds to the sampling rate, which is fs, and every index in between is just linear, right? So every FFT bin basically has a width of fs over n, where n is the number of points in the FFT. So that's why your k hat, you just multiply it by fs over n, and that gives you the actual frequency corresponding to it. Okay. Now, it turns out, so far we just assumed what you've received is coming from a single target, but this also works if you simultaneously receive echoes from multiple targets. So let's say you're sending out the ultrasonic beam pattern that you're sending is wide, and it's hitting multiple targets in the scene, and within the duration of one chirp, you receive multiple echoes, okay? That is fine. So what you have is basically a summation of a bunch of echoes, and you do the exact same thing. You down-convert them, and you take the FFT, and you're going to see multiple peaks. So this is k hat 1, and then you get k hat 2, k hat 3, and each gives you the range of one of the targets. So it also, it's very nice in that manner that if you're hitting more than one target with a single chirp, that's still fine. Your algorithm works, basically. Okay, any questions about this? All right, let's continue. So next thing we want to look at is what is the ranging resolution you get from this, and what is the maximum range that you get from this, okay? And there's a trade-off between the two. And just looking at this picture, I'm going to clean it up a little bit, and maybe also clean this up. Okay, and just looking at this, we can actually answer both questions. So in terms of the range resolution that you expect from this, it's directly tied to, again, the FFT. So the closest two targets that you can possibly distinguish in range is if they have two peaks that are exactly one FFT bin apart, right? Like one is at k, and the other one is like at the exact next bin. So that kind of is like the lower bound on how close two targets can be. If they're any closer, they basically fall into the same FFT bin, and then you cannot distinguish them, right? So that's one. And then what is the maximum range that you can detect possibly? That's where the peak is like at the very end of the FFT, right? So that's where basically your delta F hat is equal to your sampling rate. Because if the frequency is any higher than that, we know FFTs are periodic and it just wraps around, okay? So this picture directly also tells you the resolution and the maximum range resolution and maximum range that you can get. But we can also mathematically look at what they are. So for the minimum range discrimination, as I said, that you can do, that delta F min corresponds to a single FFT bin, right? And what is the width? The frequency width of one FFT bin, that's just your sampling rate divided by the total number of points in the FFT. So it's just Fs over n, okay? You can also write it as 1 over t, where remember t is your total chirp duration. Why is that the case? Because well, you have a chirp of in time it's 0 to t, and if I just draw the waveform of it, that's the chirp, and then in the ADC we're sampling it in n points, right? So you do basically discretize it to n points, so then you get this relationship between the number of points in the discretized signal and the sampling rate of the ADC and the total time duration, n equals t times Fs. Okay, so that's your minimum frequency that you can discriminate with your FFT algorithm. But what range does that correspond to? We just plug this into our range estimation equation. So our delta rho minimum, that's our range resolution. The minimum range we can discriminate is going to be the minimum delta F times the speed of sound divided by 2b. And then for delta F, we plug in the 1 over t, and we get this expression here, right? So our ranging resolution is going to be the speed of sound divided by 2 times the slew rate times the duration of the chirp. Remember this b times t, if we go back to this picture we had here, slide it up. B times T is the total bandwidth we set of the chirp, right? Because we go from frequency 0, F0, to F0 plus B times big T. And B times big T, so that's the total spectral width of the chirp, or the total chirp bandwidth, okay? So basically our ranging resolution is just the speed of light divided by 2b. So if you want more resolution, you need a chirp with a larger bandwidth, which means either higher slew rate or larger chirp duration, so larger b or larger t or both to get a larger bandwidth. That's what we need. Okay. What about maximum range? Maximum detectable range, again, as we said, it's the maximum delta F that you can find in your FFT times the speed of sound divided by 2b. And what is the maximum delta F? It's almost equal to your FFT sampling rate. So you just get your FFT sampling rate times v divided by 2b, and that is your maximum range. So here, if you want more range, what should you do? Either increase the ADC sampling rate, use a faster ADC, that's one way. Speed of sound, well, we don't have any control over that, or you can make the denominator smaller, which means reduce your slew rate, okay? So here you see two opposite effects. In terms of this slew rate, if you keep everything the same and just change the slew rate of these chirps, and remember, the slew rate is like the slope of how quickly you vary the frequency. If I want to increase the slew rate, it's going to go up faster, right? If you reduce it, it's going to go up slower. So if you just change the slew rate, what happens is that increasing the slew rate, so larger B, what it does for you is it will improve the resolution, right? Because this delta rho will become smaller, which is a good thing. That means you can discriminate targets that are more closely spaced in range. So you get better resolution, but you're going to reduce your maximum range, right? So there's always a trade-off there. That's, of course, if everything else is the fix. If you have control over some other parameters, maybe you can design your waveforms differently. But just remember that this B is a design parameter that if you're in charge of, using the sensor or tuning it for your specific application, this is one of the important design parameters. And then you need to decide what is the right choice of B that gives you the right trade-off between maximum range and the range resolution. And then you basically go with that. Any questions? Okay, so let's continue. So we talked about ranging so far and how it's done in both the case of pulse echo sonar and continuous wave sonar, right? What we have not talked about yet is how do you estimate the bearing angle or the direction of arrival for the target. Now, in terms of bearing estimation, there's different ways of doing it. For instance, some systems just use a single receiver, and from the echo amplitude that they receive, they try to estimate also, in addition to the range, the bearing angle of the target. But as we know, the dependency of the echo amplitude on the target angle, there's a lot that goes into it, right? I mean, it depends on your radiation pattern, the actual shape of the target, a lot of things. So the systems that only use a single transducers for bearing estimation, they usually cannot do a good job because there is so much uncertainty. They have to have, a signal model or a fit to the dependency of the echo amplitude to the target angle, and there's so much variation in those signal models that they usually can't do a great job. I mean, it kind of works, but it's not very accurate. Systems that can do much better bearing estimation, they typically use more than one transducer. So they use at least two, and they use this idea of triangulation that we will talk about. But before we talk about triangulation, there's a very, very interesting geometric trick that when it comes to doing the calculations for target bearing or DOA, it really makes the math a lot more intuitive and easy. And that's this idea of the virtual emitter. This is a purely geometric idea, right? There is, you know, it's not new physics we are talking about. So we're just going to, do a smart geometric trick that helps us analyze the bearing angle a little more easily in math. So when it comes to the virtual emitter, targets are very broadly categorized or divided into 3 types. And it's a very broad categorization, but it nevertheless, it's okay. It gives us something to work with. So the 3 classes of targets for sonar that are considered, it's plane targets. So it's a plane, it's kind of like a wall, just a big flat surface. Then you have corners, which is like the corner of a wall, 2 surfaces at an angle that is typically assumed to be 90 degrees. And then you have edges, right? Again, 2 surfaces, but at a basically an angle that makes an edge instead of a corner. Again, I know it's very crude, right? I mean, you can argue that, oh, but I can have like a sphere or something that is not really any of these. But very broadly speaking, in a very crude manner, you can roughly categorize different targets into these 3 categories. Now what happens, this idea of virtual emitter, let's just look at the pictures here, starting with the plane. The idea here is, so you have, let's say, 1 transmitter and 1 receiver, okay? And then you have your target. In this case, it's the plane, as drawn here. And then your transmitter receiver plane, so they are on a plane, and they make an angle theta with respect to where the target normal is. Okay, so basically the target bearing is at some angle theta relative to where the TX is pointing at. Now what happens is that the signal that goes from the TX to the RX, in this case, in the case of a plane, it's going to basically get reflected. It hits the plane and it gets reflected and it gets to the RX. And then because it's a plane, basically that main path from the TX to the RX is basically the shortest path, which, as we know from geometry, the angle of incidence and the angle of reflection are going to be equal, right? So it's kind of like as if it was a mirror. Now for this geometry here, if I place what we call a virtual transmitter, which is just a mirror image of the TX with respect to this plane, so you just basically reflect the TX and put a virtual TX here, and then you remove the plane as if it wasn't there. And now if you transmit from this virtual TX, the RX is not going to notice any difference, right? It's as if the original TX had transmitted and the plane was there, because it's the same angle of arrival and it's the same time of flight, basically, between the virtual TX and the RX and the actual TX and the RX, okay? So that's the idea of the virtual emitter or the virtual transmitter. It's a purely geometric argument. Now you might ask, what's the use of it? I'll show you in a second. But just to complete, if it depends like where the virtual transmitter is, it depends on the geometry of the target. So if it's a plane, as we saw, you just reflect the transmitter relative to that plane. If it's a corner, your virtual TX is going to be the reflection of the transmitter with respect to basically the corner point, right? So you basically reflect it, you put your virtual TX here, and then from this virtual TX to the RX, it's going to see basically as if it was the actual TX, the same DOA basically. Finally, if you have an edge, your virtual transmitter, it would be the edge itself. That edge point becomes basically the virtual transmitter. And one point to note about edge targets is that, as we said before, when you have edge targets, the echoes that reflect back, they're going to be spherical waves because those essentially act like point targets that are very small, and then they echo back spherical wave fronts to you. Okay, so that's the idea of the virtual emitter, purely geometric, right? Nothing really physically new about it. But why is it useful? It's useful because it lets us to do DOA estimation basically very easily. So as I said, the type of DOA estimation we are going to look at is going to be based on triangulation. So in this case, you have at least two receivers. Okay, so I have RX1 and RX2. They're separated by some distance d. Okay, and they have received echoes. And let's say we know the echoes that are received by the two RXs correspond to the same physical target, okay? But they're going to, because they're located at different positions, the range that the two receivers estimate, the rho, is going to be different, right? So RX1 is going to estimate some range rho1, and RX2 is going to estimate some range rho2, right? But now we can assume both of these are coming from the same virtual transmitter. So I had one transmitter, two receivers, a target, okay, doesn't matter what it is, but whatever target it is, we can make an equivalent, basically, geometry here, which is a virtual transmitter and the two RXs, okay? And now the DOA estimation problem is, what is this angle theta, basically, relative to, say, RX2, and that is the DOA to the actual target, because we know the DOA to the virtual TX is going to be equal to the DOA to the physical target, okay? But now we have a very simple geometry, basically, to solve here, because basically, we look at, we have multiple triangles here, but if you look at this one first, that I highlight in green, in red, the sign of the DOA is going to be given by d plus h over rho 2. The d is the separation between the Rx and Tx. H is this additional piece basically here. It's a right triangle, right? So d plus h divided by rho 2, that's sine theta. Cosine theta is L over rho 2, right? And then we can look at this top triangle. I'm going to highlight it in purple. And then in there, we see that h is equal to square root of rho 1 minus L squared. I mean, this is pure, Pythagoras theorem and geometry. But basically, from these three equations, we can solve for theta. And theta becomes this, the arc sine of d squared plus rho 2 squared minus rho 1 squared over 2d times rho 2. What's nice about this is everything is known, right? D is the separation of the two receivers. We know what it is. And the rho 1 and the rho 2 are the ranges that the two receivers estimated. Okay? You just plug everything into this. You take the arc sine, and that gives you the DOA to the target. So very simple. But what's important about it is that you need to know the rho 1 and the rho 2 that you measured with your two receivers correspond to the same target, right? If they don't, well, this argument is invalid. And that's okay if you just have like one target in the scene, then of course, yeah, I measured two ranges, they correspond to the same target. But when you have a very cluttered scene, and then you simultaneously receive echoes from many targets, establishing that correspondence between the rows that your different receivers are estimating becomes a difficult task. So that's one thing to note. The other one to note is that, well, this method works and it's often used, but it's important to note that it couples your bearing estimation to your range estimation, right? So whatever errors that you have in your range estimation would now get into your bearing estimation or DOA estimation. So if you use a poor method for ranging, like a threshold-based ranging, which can have a very large error, then that error basically propagates into your DOA as well and can make your DOA very, very inaccurate. Okay, one simplification we can do to the expression we had in the previous page is that if the receivers are placed very close to each other, so if that separation d is much smaller than the distance to the target, row 1 and row 2, basically the expression simplifies because you can basically ignore the d term in the numerator and make it simpler. So then your bearing estimate basically just becomes arc sine of row 2 minus row 1 over d. Very, very simple expression. Okay? Any questions about DOA estimation? And this is general, right? This is independent of, like, do you have a pulse echo sonar or a CTFM or how you're doing your ranging? It doesn't care, right? All you need is 2 receivers, 2 range estimates, and know that those 2 range estimates are for the same target, and the rest is just geometry, right? So hopefully now it makes sense why we introduced this idea of the virtual TX or the virtual emitter, because basically this picture is why, right? This I lost it. This picture is why, because with the virtual TX, you just take the target out of the picture and you just have a very simple geometry to solve for DOA estimation. That's why. It just simplifies the math, basically. Okay, so let's continue. As I said, so what kind of accuracy you can get with this triangulation, basically, technique? You can get sub-degrees. I mean, in a good day, where your environment is not cluttered, your SNR is good and all that, you can get close to like 0.2 degrees or a little better. So that's like what to estimate. If things are noisy, if you have too much clutter, you can do worse. But that's what you could get. As I said, there are methods for bearing estimations that just use a single transducer. But those methods need, a signal model, essentially, which is usually those are data-driven techniques which do a fit to the echo amplitude as a function of bearing with a bunch of assumptions basically baked in, and then they use that to do bearing angle estimation. And those methods are not very accurate. So they can get at best to like 1 degree accuracy or so. And it sort of makes sense why, because there's too much variation in the signal that a single receiver would receive as a function of bearing and other parameters. So just the data-driven approach can only get you so far when it comes to having a signal model to work with. But triangulation, you can do much better. You can even do triangulation with more than 2 receivers. I mean, you can have a bunch and even reduce your error even further. But 2 is sort of the minimum. You've seen this. I mean, the lots of cars, many cars today, they have ultrasonic sensors in their bumpers. And some of them just use there's typically 4 in the bumper. And some of them just use them individually and for just ranging. So they just beep if something is close to one of the sensors, and that's all they do. Some of them do something more advanced. So what they have is that they have transducers with radiation patterns that kind of overlap. So this is one, this is another one, this is another one, and this is another one. And when the target is close, it overlaps more than one antenna, so they can basically triangulate it. So they do like a row 1 to your first transducer and a row 2 to the second transducer, and find actually not just the distance but also the bearing angle of the target. And they actually can build like a very crude kind of like a map around the car in close proximity. And the cars that actually, the more fancy cars that, for instance, have automatic parking function, those should do this, because if you want to actually automatically park the car, just a proximity is not enough. You need to build, a mini map around the car. Cameras are not great at very close range because of just the physical limitations of how you can place them around the car. So ultrasonic are very good for this. It's an application that is a great fit for ultrasound because you need close range sensing. You are not typically moving very fast, right? Things are slow, so it's okay if your sensor is a little slow, and you need a solution that is cheap and robust. So ultrasonic sensor is a great choice for that. Questions? Okay, so there's something really, really cool and unique to sonar when it comes to bearing angle estimation. Which is you can actually do a classification of targets just based on DOA, okay? I mean, when we hear classification, we typically think about, vision sensors like cameras with, fancy neural networks that do classification. And those are, of course, the best classifiers out there that can do very sophisticated types of classification. But it turns out that an ultrasound sensor can do a very crude classification for you almost for free. So it's just a fun thing to look at. And it's purely, again, a geometry-based argument. So here, what you need is 2 pairs of transducers, TX, RXs. So 2 transmitters, 2 receivers, okay? That's the assumption. And what you do is, first you transmit with the first transmitter, TX1 transmits, and then you measure a DOA theta 1, and then you transmit with TX2, and you measure another DOA theta 2, okay? And just by comparing the 2 thetas, you can distinguish the 3 types of targets we talked about, which is planes, edges, and corners. And this is how it works. Again, pure geometry. Let's look at the plane case. So I'm writing these as TRX because it's like a transmitter-receiver, combo thing, co-located transmitter-receiver. So that's TRX1, TRX2. So each is both a TX and an RX. And what we're doing, let's say first TX1 transmits, and what DOA do we measure? And we are also looking at DOA on RX1, let's say, okay? If it's far away, it doesn't matter which one you look at, but let's say we're just looking at RX1. So TX1 fires, right? What DOA do you measure? Well, we should look at the virtual transmitter corresponding to TX1, which is the mirror image of that relative to the plane. So that's number 1, right? And what DOA do you measure? Well, we measure theta 1, right? I'm going to highlight it in red. Okay, so that's your theta 1. Then TX2 fires. What is the virtual transmitter for TX2? Highlighted in orange, that's number 2. Again, you just reflect TX relative to the plane. So that's number 2. And what DOA do you measure with 2? You measure this larger angle, highlighted in orange, theta 2. Right? So if you compare theta 1 and theta 2, or if you look at their difference, which we call psi, which is theta 2 minus theta 1, you see it's a positive value. Okay, well, so what? The so what, it becomes clear if you look at a different class of target. So if you look at a corner, for instance, I'm not going to do the full walking through the geometry because it's kind of obvious. But again, you do the same thing. You first do the TX1, look at the corresponding virtual TX, so it's going to be up here, and for TX2 it's going to be down here, and then you look at the theta 1 and theta 2, and now you see for this type of target it's the exact opposite, so theta 2 minus theta 1 becomes negative for a corner. And if you do that for an edge, you would see that the theta 1 and theta 2 become equal, which is pretty cool. I mean, it's very limited what you can do with this, right? But it's kind of interesting that just by pure geometry, you can do like a very simple classification in sonar. I thought it's just cool to point that out. So you just, again, have 2 transmitters, 2 receivers, do your DOA estimation twice, and just by that delta difference in the angle, you can do a bit of classification. Any questions? Yes?
Just trying to say, The varying angle, my understanding was that the angle between the transmitter and the receiver was the same. In the first case, shouldn't theta 1 be 0? And it's just
First case, is it the plane you mean, or why would it be 0? Could you say that again?
The varying angle would be the angle between the virtual TX1 and TRX1, right?
Yeah, but when we talk about the angle, remember that, remember that there is a plane here, right? So our TXs and RXs have their normal, which is this, highlighted. Okay, so the angles are relative to that. If it was directly pointing to the plane, yes, we would measure 0, but not when there is an angle. Okay, so last part about sonar is basically this idea of ego motion effect. So this is a big limitation of ultrasonic sensors, which basically boils down to the fact that the speed of sound is not that high. Okay, it's like 340 or 30 meters per second. So what can happen is that if your sensor is mounted on a platform that is moving, a robot that is moving, okay, and that's what we mean by ego motion. So if the sensor moves, what can happen is that when your transmitter transmits a waveform, by the time the echo is received back, you are at a different position, right? And that position, well, you might think, oh, but we can ignore it. Well, it turns out that no, it's not negligible. Even if you're moving at like a few meters per second, which is 1% of the speed of sound, that effect can be significant. So by the time you receive the echo, your platform has moved enough that that movement is going to cause errors in the range and the bearing angle estimation. Okay, so that's the idea of ego motion effect. And it depends on a few factors. One is, of course, the movement or the velocity of the robot that the sensor is mounted on. The higher the velocity, the bigger these effects are. The type of motion also matters. Typically, linear motion is much worse than rotational motion. Rotational motion is usually not too bad, except if it's at very high angular velocities. But linear motion, again, even like a few meters per second, you can get like a 0.6 degree bearing angle error up to that, which is significant, right? And also, the effect depends on the geometry of the target. So again, a plane versus an edge versus a corner affect differently, both when it comes to ego motion, the range and the bearing, okay? So sometimes you can have algorithms that compensate this effect to some extent, but the algorithms tend to become a bit too complex and also not perfect. So oftentimes they're not actually used. But just know that in algorithm you can compensate to some extent the ego motion. Now, the exact effect that ego motion has on the range and the bearing angle, you can calculate it for every type of target. And in fact, it is done in the notes. But I'm not going to bore you with it because it's purely geometric arguments, and I'll let you read it in the notes. It's very detailed derivations for every type of target. But just set it up for you so you know if you read this how the calculation is being done. Basically, we look at different types of targets, starting with the plane, okay, and we assume there is a transducer that is moving at some velocity u. So at the time of transmit, it's at this position highlighted in red, and by the time it receives the echo, it's at this purple position. So it basically moves by this much from the time it transmits the wave to the time it receives the echo. So basically, the round-trip path of sound is, for the plane case, is this, right? And then
as usual, we have our frame of reference. That's the x-axis, that's the y-axis, and the velocity is u, so it has an x component and a y component. Okay. If the platform was a stationary, it would stay just at this point. What it would measure in terms of the range to the target would be d, right? D is this distance, so it would just hit the wall and come back, and your sensor would be at the same place, so it would measure d. Now, because it is moving, it's going to measure a different range and a different time of flight. You can exactly solve for that, and again, I'll let you read the math because it's pure geometry, but for instance, for the case of a plane target, it comes to this, which is the time of flight that you measure is going to be, this tau 0 is the time of flight with no ego motion. So if your transducer was a stationary, but now because of the ego motion, now you have this dependency on the x and the y component of your ego velocity. And in this case, in the case of a planar target, depending on what ux and uy are, you can measure a time of flight that is bigger or smaller than tau 0, which is the stationary case, which kind of makes sense. If you're moving towards the wall, for instance, you're going to measure a shorter time of flight. If you're moving away from it, you're going to measure a longer time of flight. So the point here is you can exactly calculate them just from geometry, and you can, because you can calculate them, you can come up with algorithms to compensate them to some extent, and it's also highly dependent on the velocity and the geometry of the target. You could do the same calculation for angle of arrival. Again, it's all in the notes. I'm not going to go through it all because it's kind of a thing you need to kind of sit down and, you know, at your own pace go through it. Otherwise, it becomes very dry if you do it here. Any questions? Okay, so we are pretty much done with the discussion of sonar. I just want to kind of summarize it all. So we learned about the physics of sonar, you know, the system architecture, different type of waveforms, how you process them, how you estimate range and bearing. And as we did this, we also learned about all the limitations of sonar sensors. So very specifically, for instance, if you have wide beam patterns, those can affect in poor bearing resolution. We know that the sensing rate is not going to be very high in sonar because you're basically limited by the speed of sound. The range is limited because of the high attenuation of factor of sound waves in air. We also know if you have smooth surfaces at very oblique angles, you might not receive any echoes from them because most of the sound that hits it is going to bounce off away from you. So sonar typically has a hard time detecting targets at oblique angles. You can have false detections because of, you know, large side lobes in your beam pattern or, you know, other non-idealities in your signals. Just to make matters more complicated, humidity and temperature variations in air cause changes in the speed of sound. And every calculation that we did, as you saw, for ranging and bearing angle estimation, the speed of sound goes into those equations, and you always assume some constant for it. And if that constant doesn't change what the physical speed of sound is, that's an additional source of error. So all in all, what kind of performance can you expect from kind of your sonar sensor? Maximum range, 10 to 15 meters, I would say. And again, these numbers are not set in stone. Like, I'm sure you can get more than this with some effort. But these are, you know, typical numbers to expect from a good sonar for robotics. Range resolution, few centimeters up to like 10, 20 centimeters. Bearing resolution, depending on how you do it, you can do 0.2 degrees to maybe 1 degree, and you can do about 10 to 40 measurements a second. Okay, so I mean, if you look at this slide, you're going to see like everything here is like a negative, right? So these are all, you know, limitations. But I hope this doesn't come through as, okay, so sonar is useless. No, that's by no means the case. It actually can be very, very useful. It all depends on your applications, right? What are you trying to do? And what type of autonomy you're trying to do, and what are the constraints you need to work with. And actually, Sonar can be a perfect fit. So that, like automated parking, for instance, is one case where Sonar is a very, very good fit. So typically, if you're in short-range cases, you don't have very fast ego motion, right? Things are kind of stationary or moving slowly. You don't need like crazy high angular resolution, and you don't need crazy high measurement rates, but you're looking for something reliable and cheap with not a lot of power or compute resources. Sonar can be perfect. Okay, let's look at one simple example of how sonar mapping works in action in robotics. If I can open this link. Okay, before I play this, what you're about to see, it's a little dark, but let me actually go to here. So it's a room that is being videoed from the top, okay? And then there's this little robot thing that is moving around the room. And there is some objects. You have a box here and a box here and a wall and another little box in the center. And it has one sonar sensor mapped on it, mounted on it, and it's going to map the room as it moves around. Okay, so it's a mapping application in robotics.
This arena for our robot. We place two objects in the corner and a glass object in the middle of the arena. The
I can't stop the audio,
consist of 3 wall panels and 1 glass surface. As the robot.
So here they're showing basically the live output of the map that is being generated by the sonar sensor. So as it does a ranging and a bearing angle estimation, it puts one dot in this 3D plot. Basically, each is a target that it is detecting.
Navigates the arena. You can see its 3D range data being published on the point cloud.
So that's the kind of speed that you get. It's a slow, right? It's not the fastest. It's not crazy high resolution. But again, it could be useful. I mean, if you give it enough time, it's going to build a decent map. I'm going to fast forward a little bit. So you see, it's kind of towards the end.
After the robot is done, we get raw data points describing the complete arena. If
I stop here, I mean, it's not bad, right? It got so that's one of the boxes, that's the other box, that's the thing in the center. A lot of false positives, right? Like stuff around here, these are all false positive. Some stuff it detected behind the walls, those are false positives. So it's not perfect, not super high resolution. Nevertheless, it could be pretty useful. I mean, these things are going to be very cheap, very low power, very low compute. Okay, one more thing to note before we close the chapter on sonar is that the type of sonar we talked about, everything we talked about, was very targeted to robotic autonomy applications. In other applications, you can have sonar with different transducer designs, different type of DSP, different frequencies, and then you get very different types of outputs basically from them. Medical applications is one, right? As we said, those operate at much, much higher frequencies. Range is much shorter, but that's okay for medical applications. Because they're at high frequencies, they can have much smaller transducers and many more of them. So they have big arrays of piezo or MEMS transducers, and then they can get much better angular resolution, for instance. So the numbers that we're talking about, if you talk to a person who works in medical sonar, they might say, oh, what are you talking about? We can get 10 or 100 times better than this. Yes, for that application, because they're working with, at different frequencies, with different, constraints. For robotics, these are the ballpark numbers that you would estimate. Another type of sonar, which is actually very common, not for robotic autonomy, but in other fields, is they do sonar underwater. And the idea is called synthetic aperture sonar, where they actually very slowly move their transducers. And with some very clever techniques in signal processing, they can effectively generate virtual apertures that are much larger than the physical aperture. And as we know, the beam width goes inversely with the aperture size, so they can, in DSP, basically synthesize this very tight sonar beams underwater. And then with that, they can do extremely high resolution images like this one that you see. It looks like just a picture, but it's actually a 3D image. It has depth information. So it's a ship from World War II that was sunk, and it was a Norwegian tanker. And this is a sonar picture of it, extremely high resolution. But this picture, this can take hours to collect all the data, because they're very slowly moving their transducers underwater. It also requires very high amount of compute to generate. It's all done in post-processing. So it's not like live view, you're going to get this image. No, this is hours of data collection, maybe another hour or two of crunching the data, and then eventually you get this. Again, not useful for robotic autonomy, but just so you know, sonar in other applications can do very high resolution things. Any questions? Yes.
Yeah, but why sonar can achieve high resolution? Like radar also uses the FMCW, but why it cannot achieve the wavelength or some reason?
So the question was why sonar cannot achieve high resolution. Was that the question, or?
Why sonar can and radar cannot?
Oh, actually, radar also can. So when we talk about sonar resolution, first, radar can do better resolution than sonar, right? It's all about, and by resolution, are we talking about angle resolution or range resolution? Or angle resolution, okay. So for sonar, we said like 0.2 degrees or so, right? Yes, you can do that for, again, on a good day, right? Like you have good SNR, you don't have a very cluttered scene, everything looks good, and you can achieve that. Radar also can approach that with better algorithms. I mean, we haven't talked about radar yet, but when we talk to it, with better algorithms, like if you use super resolution DOA algorithms in radar, you can do even better than like 0.2 degrees. It really boils down to two things. For radar, how big is the aperture, and what type of signal processing algorithms you can do. I know my answer is a little vague right now because we haven't talked about radar, but when we do, remind me of this question, and we can talk about the resolution limits for radar. But it can get close to this or better, yeah. Okay. Other questions? All right, so now we can start talking about radar. So radar is another active sensor used for robotic mapping. And the main difference with sonar is basically it uses electromagnetic radiation instead of waves, instead of sound waves at radio frequencies. So it can determine range, it can determine angle or direction of arrival. As we will see, it can also detect the radial velocity of targets using the Doppler effect. A little bit of history. So the concept was proposed in early 1900s by Heinrich Hertz, but the actual first deployment of radar was fueled by basically World War, the Second World War, similar to many other technologies that basically they were developed during the war. So the first field deployment of radars, it was what was called chain home radar at the time, and it was built by the British Royal Air Force and deployed in 1938. And chain home was a fascinating thing. So it was basically a number of radar antennas that were built along the east coast of United Kingdom. It was operating at a frequency of between 20 and 30 megahertz, and it had a pretty long range. It could detect up to 99 miles. And it was purely designed and built as an early warning system for basically the German aircrafts that could come and attack the UK. And it was one of the main reasons that Germans actually never successfully attacked the UK during the World War, because the chain home did such a nice job of the early warning. So they had 21 sites along the coast. And here's a picture. So the antennas were huge towers, 360 feet tall, and each transmit antenna was basically 2 towers, and the actual antenna was basically hanging from the 2 towers. It was like a dipole antenna structure, huge thing. Receive antennas were smaller single towers, and here on the map you see each dot is basically one of these. And here's a picture of one of the sites. So they had 21 sites. It was a huge effort, right? Fun part, at the time, essentially there was no digital signal processing. So the signals were processed by humans. So they were basically collecting these signals from the radars in real time, and they had these offices full of engineers looking at the signals and trying to figure out what is the range and what is the DOA. Fascinating, but it actually worked. So that was radar in 1939. Today, it's everywhere. I mean, from astronomy to medical applications to robotics to aviation, even like as you go to the airport, this fun little things in the airport security which have you do this and then it rotates around you. There's actually a big radar antenna array in them. It doesn't show the actual output, but these things have extremely high resolution. So when you stand in there, the device is actually doing a very high resolution picture of you, and if you're concealing something, it can detect it. The actual output that it shows the TSA agents is not this. It just highlights part of the body if it thinks something is there. But it's actually a super, super high resolution radar, this thing. Cars have radars today, you know, just the collision avoidance and other things. But it's everywhere, modern day radar. It's really deployed very widely. So we're going to do the usual thing, start with the physics. Right, as you know, and the physics of radar, of course, we're going to talk about electromagnetic waves and also how antennas work, basically. And then from there, we're going to talk about the system architecture, how you do ranging, how you do angle estimation, how you do velocity estimation. And also, along the way, just like we did for sonar, we do a little bit of taxonomy of, you know, different types of radar. It's going to be our biggest chapter in the course, so we will probably spend something like 5 lectures on it, for a good reason, because radar, I think, is well, as I said, it's been around for a long time, right, since the 1930s or so. But it's really very recently that people started paying attention to it as a very useful sensor for autonomy in robotics. All the previous work on radar was very driven by military aviation and astronomy. So a ton of progress has been made there, but for very different types of applications. So very different types of radars have been, you know, designed. So the type of radar that, for instance, you use in an airport or on an airplane or on a tank, it's not useful for robotics. It's useful for those applications. So that's why for radar in robotics, it's still an extremely active field of research across the board, from the hardware design to, you know, the algorithms, signal models, simulation. You know, there's a lot of very interesting work being done here. And I think it's one of those sensors, or probably the main sensor for robotic applications, that we're still, in my opinion, about like 10 to 20 years away from it getting to the full maturity level. And by maturity level, I mean like maybe the gold standard is something like cameras. Digital cameras are extremely mature these days. I mean, you can buy them cheap and robust and, you know, extremely good performance. Radars, again, for autonomy robotics, they're not there yet. We've made a ton of progress, but it's still a very hot, active field, and that's why I want to really spend the time on it and really give it the attention it deserves. Okay, so starting with the physics, the radars use electromagnetic radiation. So these are waves that propagate in free space, and they can be at different frequencies. Radars use RF, radio frequency waves, and then later when we talk about LiDAR, it's the exact same physics, just at much higher frequency, and that's optical frequencies. That's where light is. But the physics is the same. It's electromagnetic radiation, and typically you have an electric field, we call that E, and a magnetic field called H, and these two fields are always coupled and propagate together. And in many applications, as we'll see, they're actually the field vectors are orthogonal to each other, as shown here in red and blue. And just like acoustic waves, they have a wavelength lambda, and also you have a direction of propagation. So they're traveling in a certain direction in free space. Okay, so the electromagnetic fields, as you might remember from physics course you've taken, the physics of them is governed by the extremely famous Maxwell's equations, right? So Maxwell's equations is a set of 4 differential equations that pretty much completely, you know, describes the physics of electromagnetic waves. And the equations are in terms of the electric and magnetic field. Very specifically, they say that the divergence of the electric field is equal to rho, which is the charge density, electric charge density, divided by epsilon, which is a constant, and it's the permittivity of the medium. Then they say that second equation is divergence of H equals 0. So H is a divergence-free field, as we say. Then we have the curl of E, which is equal to a constant times the time derivative of H. Okay, and that constant mu is the permeability of the medium. And finally, we have the curl of H, which is equal to J, which is the electric current density in the medium, plus the permittivity times the time derivative of E. Okay, so what matters for us here is really the important thing is, as these 2 last equations show you, there's 2 things that can give rise to electromagnetic radiation. One is if you have a time-varying magnetic field, so if this partial H, partial T term is non-zero, that gives rise to an electric field, right? Because then the curl of E becomes non-zero. And also from the last equation, we see that if you have a current distribution that can vary with time, that can give rise to a magnetic field, or if you have a time-varying electric field, that can also give rise to a magnetic field. So that's why the electric and the magnetic field always go together, because if one of them is basically radiating and is varying with time because of the Maxwell's equations, the other one also has to be non-zero. And just to remind ourselves, what is the divergence and the curl? These are just from calculus. We know the divergence of E. And remember, E and H, these are vector fields, right? So these are fields in R3, right? So they have an X and a Y and a Z component. And the divergence of E, it's a scalar value, which is just the sum of the 3 partial derivatives of E with respect to X, Y, and Z. So divergence of E is just a scalar, right? And the curl of a field is given by this bigger expression. It's also related to its partial derivatives with respect to X, Y, and Z. But the curl is a vector, right? It's a vector in R3. So that's just a mathematical definition of a divergence and a curl. I think this is a good place to stop because we're almost out of time, and then we'll continue next time. Any questions? No? All right.